Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. Today we are going to discuss about the module Design of Silicon Solar Cell from the paper Energy Related Materials. So students, let us discuss the main points which will be covered in this module. First, we will discuss what is a silicon. Second, how it is extracted and purified. Third, what is the difference between MGS and SGS. Fourth, what is cell design? Lastly, we will discuss what is a cell module. Let us start with a brief introduction about the module. Amongst all semiconductors, properties of silicon are widely known, and conceptually, homojunction solar cell is perhaps the simplest structure of all photovoltaic devices for terrestrial applications. Silicon material was first discovered at Bell Laboratory in 1953. It was used successfully in solar cell in 1995 to powering a telephone repeater. The name silicon, adopted from the Latin word silex, and it is the second most abundant element in the Earth's crust. Later in 1906, silicon was used in electronic industry in point contact rectifiers and in microwave detectors in 1930. So, the purification of silicon materials is necessary before their use in device fabrication. Silicon purification technique was first discovered in 1950. In 1950, a single crystal silicon was grown using Czochralski method. In order to develop an efficient solar cell, a high purity polycrystalline ingots with impurities less than 10 to the power 18 atoms per meter cube is required. So students, let us discuss about the standard technology stages for making the solar cells. First stage is the reduction of sand to metallurgical grade silicon, that is MSG. Second stage is the purification of MSG to semiconductor grade silicon, that is SGS. Next stage is to convert this SGS to single crystal silicon wafers. Next is to process this SGS wafer into the solar cell. Finally, we will convert our solar cell to the solar module. Transformation of sand to metallurgical grade silicon MGS. The source material for the extraction of silicon is silicon dioxide. which is the key constituent of sand. Initially, the silicon dioxide SiO2 is reduced to silica by carbon in the form of a coal or a coke. The reaction which governs this process is SiO2 plus 2 carbon gives Si plus 2Cu. So the silicon is periodically poured from the furnace and blown with oxygen or oxygen chlorine mixture, and finally it is solidified. The produced silicon is about 98 to 99% pure, with major impurities like iron and aluminium. The so produced silicon, designated as metallurgical grade silicon or MGS, because it largely used in steel and aluminium industries. This MGS required further purification to convert it into semiconductor grade silicon SGS for electronics industry application. The typical concentration of impurities in MGS is given in this table. So as you can see from this table, that is for each impurity, a particular concentration range in the units of parts per million has been specified. And the iron impurity is the maximum concentration range parts per million impurity in MGS. This MGS required further purification to convert it into semiconductor grade silicon SGS for electronics industry application. The transformation of MGS to semiconductor grade silicon SGS. There are various procedures of purifying MGS to SGS, but the most standard method is the Siemens process, in which the MGS is converted into a volatile compound that is condensed and then refined by fractional distillation, which is shown in the figure also. The extremely pure silicon is then taken out from this refined products. The detailed procedure is that a bed of fine MGS particles is fluidized with dry HCl gas in the presence of copper as a catalyst at about 240 degrees Celsius to simulate the reaction. A mixture of SiHCl3 of 80 to 90% is obtained, and the reaction which governs this process is given below, that is Si plus 3HCl gives SiHCl3 plus H2. The gases emitted passes through a condenser and condensed. The resulting liquid is subjected to multiple fractional distillations to produce SGS SiHCl3. This is the source material for silicon semiconductor industries. Further, in order to extract SGS, SGS SiHCl3 is reduced by hydrogen. The silicon in the fine-grained polycrystalline form gets deposited on R-finduction heated silicon rod at about 1100 degrees Celsius according to the following reaction. That is, SiHCl3 plus H2 gives Si, that is silicon, plus 3HCl. This process of preparation of SGS is a high temperature, slow, and a batch process. Also, it has a very low yield. Hence, the final product becomes expensive due to the use of very large amount of heat used. This ultra-pure polycrystalline silicon is finally to be converted into the single crystal form for its further use in the fabrication of solar cell. Polycrystalline SGS to single crystal wafers. There are numerous methods of growing single crystals of silicon semiconductor, which includes Czochralski's technique, heat exchanger method, shaped ribbon technology, the dendritic web method, silicon on ceramic method, CEMIX method, etc. So students, we will be discussing all these methods one by one. First, let us discuss the Czochralski process. This process is one of the most advanced used methods for growing silicon single crystal, and it has been shown in the figure. In this method, a small amount of polycrystalline SGS is placed in a quartz crucible, which is kept into a vacuum furnace to melt the polycrystalline silicon at a very high temperature. Now, the traces of dopants are added to use it in the device fabrication. For silicon solar cells, boron, that is p-type dopant, is normally used. Now, using a seed crystal of solid silicon into the surface of molten silicon and slowly pulling the seed in the upward direction. In this way, it is possible to pull out a large cylindrical single crystal of silicon. These large cylindrical silicon single crystals of size about 12.5 centimeters in diameter and 1 to 2 meter in length are removed from the furnace and later cut carefully using the diamond cutter to avoid any wastages into the thin wafers of about 0.2 to 0.5 mm thick. However, the cutting of the wafer is quite difficult, which results in the wastage of silicon crystals. Generally, saw blades used to cut the silicon crystal have same thickness to that of the wafers, and therefore 40 to 50% of the material gets wasted in this process. Moreover, the wafers got damaged while slicing, which needs to be cleaned by acid etching. More often, The sides of these circular wafers are clipped to get either a square or hexagonal shaped cell to have better packing density in a solar cell module. This process for transforming the SGS into the single crystal silicon and then cutting it into the wafers is very difficult and a serious work. Now let us discuss the other techniques of converting the SGS to single crystal wafers. First is the heat exchanger method, HEM. It is also known as the directional solidification casting method, which produces low-cost silicon, and it is comparatively a newcomer process which needs to be modified. In this method, the SGS is kept in a square quartz crucible placed in a constant temperature hot zone. The directional flow of heat from the hot ingot to the exterior being done by a gas-cooled heat exchanger base plate where the crucible is placed. A single silicon crystal seed is used for the crystal growth at the bottom of the crucible. Control heat transfer arrangement is made to avoid to the melting of crystal seed, and a graded silica crucible is used to avoid the heterogeneous nucleation at the crucible walls. In this process, a block of a silicon with side 30 to 35 centimeters can be produced, which is a single crystal except for around the edges. Finally, the square wafers can be sliced from this square rod using normal methods. This method is able to produce large amount of silicon single crystal. The next technique is the ribbon technology. Ribbon technology of growing the single crystal silicon is also known as the edge-defined film growth technique, in which the ribbons of single crystal silicon of about 10 to 12 centimeter wide are produced. This technique avoids the material wastages in slicing and polishing of wafers. In this process, a carbon capillary dye partially dipped in the molten silicon is used, through which silicon goes up and is pulled out from the top of the die in a flat ribbon form. The shape of the silicon ribbon can be controlled by the shape of the top of the die, the temperature, pulling rate, and the surface tension. As the silicon ribbons produced in this process are very thin and smooth, wafering and smoothing are not required to produce a single crystal silicon. At present, this technology is one of the least expensive technique for producing the single crystal silicon. The next technology is the dendritic web method, that is WEB. In this method, a single crystal silicon ribbon of about 4 cm wide and 0.1 mm thick is produced from the molten silicon without using a dye material. It has two parallel dendrites which are dropped into the liquid silicon and then slowly withdrawn. The capillary action forms a network between the two dendrites, which on solidification generates a single crystalline form of silicon. The crystals grown in this method are better and they are 1-1 oriented compared to that grown by capillary method. Both the techniques, that is WEB and EFG, of growing single crystal ribbons, they have advantages and disadvantages. The next technique which we are going to discuss is silicon on ceramic SOC method. This technique, that is the silicon on ceramic method of growing large grained polycrystalline sheet of silicon, was developed by Hornwell Inc., where a ceramic substrate is used to grow the crystal silicon from the molten silicon. In this process, the ceramic material is coated with the carbon on one side and is exposed to molten silicon and moved at a constant rate, leaving a thin sheet of silicon. This ceramic substrate is slotted to provide the electrical contact to the other side of the silicon. The next method which we are going to discuss is the CEMIX method. This was established by Solarex Corporation of USA, which provided the microcrystalline silicon to solar cell industries. The method by which multicrystalline silicon is grown is known as CEMIX method. This method uses a low-cost container instead of expensive quartz, which gets crack while cooling, where the molten silicon is poured. In this process, a uniform temperature is maintained for allowing the growth of sufficiently large crystals with better electrical properties. Further, this material is sliced into large wafers. The cells made from this material have shown the efficiency of about 10%. The next process is the zone refining process. In this process, the polycrystalline material can be grown on a rod or a ribbon as desired. This is a crucible-free process where the polycrystalline ribbon or rod deposited by chemical vapor deposition. The liquid silicon is held in position due to surface tension and shapes the feedstock decides the final shape of the grown crystal. This process purifies the material and single crystals are obtained. Surface preparation. The surfaces of the crystals grown by many techniques are not smooth and there are little damages at the surface. The smooth, clean and damage-free wafer surfaces of silicon can be obtained by chemical etching, which improves the cell efficiency and durability. Chemical etching can be achieved by using acid or alkaline etchants. The chemical etchants mostly used are nitric acid, CH3COOH, and HF, all of which provide good results on both, that is 100 and 11 surfaces of silicon. The less expensive and most common etchant is alkaline etchant. However, it is orientation dependent and shows good for 100. Metallic contaminated impurities from silicon surfaces can easily be removed using dilute solution of HNO3 or HCl.
Dopants diffusion. The electrical properties of silicon depends on the nature and the amount of doping materials. The dopants with suitable energy levels, better solubility, and appropriate diffusion constant are highly suitable for silicon. There are many dopants which can be used in the silicon crystal. Boron and phosphorus are the most widely used acceptor and the donor dopants for silicon for both the terrestrial and the space applications. The excess concentration of dopants in a semiconductor reduces the electronic mobility, decreases the minority carrier lifetime. Generally, in most of the crystal growth techniques, the boron is always added in the molten silicon, which results in the p-type wafers. Then the N layer on the p-type semiconductor can be obtained by diffusing a donor concentration into the p-doped semiconductor layer, exceeding the density of acceptor there by growing an additional N-doped layer. This N-doping in semiconductor is achieved by several ways. Generally, the p-n junction is made by the diffusion of dopants. In this process, the phosphorus oxide is used as the diffusion source and oxygen is utilized to transfer the dopants onto the silicon wafers stacked in a furnace. So a carrier gas is bubbled through the phosphorus oxychloride mixed with a small amount of oxygen and is passed down a heated furnace tube in which the wafers are stacked. This grows an oxide layer on the surface of the wafer containing phosphorus at the temperature of around 800 to 1000 degrees Celsius. The phosphorus diffuses from the oxide into the silicon wafers. This makes the silicon wafer N-type on the surfaces. So after about 20 minutes, the p-type impurities overrides the boron impurities in the region near the surface of the wafers to give a thin, heavily doped N-type region. After that oxide layer is removed, from all sides except the front. This method is widely used to fabricate the N-type and P-type silicon. However, this method has disadvantages. It is a batch process, it is costly, requires huge energy, and the diffusion occurs on both the sides of the crystal. So the uniformity is that they are having shallow junctions. Now, as you can see from this table, this shows the different dopants which are used in the silicon and when they are added into the silicon, which type they will make, and the energy from the valence band, the energy below the conduction band is also being tabulated. The figure shows the donor and the acceptor concentration, that is Ne and NH, affects the mobility and the lifetime of minority charge carriers significantly. So a graph has been plotted between the hole mobility versus the acceptor density and the electron mobility versus the donor density. So here it can be seen that the mobility of charge carriers remains constant up to a donor or acceptor density of 10 to the power 16 centimeter minus 3, after which it decreases faster in the case of electron mobility and a little slower in the case of hole mobility, with the further increase in the dopant's concentration. Additionally, huge concentration of dopants causes decrease of minority carrier lifetime because of lattice distortion. Dopants diffusion. Another recent technique is ion implantation for the dopants diffusion, which is more controllable in both the penetration depth and the doping level as compared to diffusion. Also, the bombardment rate can be made quite high in ion implantation. The damage produced by the bombardment can be removed via thermal annealing, an electron beam, or a laser beam. Ion implantation shows excellent results for solar cell with efficiency in the range of 14 to 16%, which is comparable to the results observed in case diffusion method. However, the disadvantage of this process is the high cost of ion implanter. Diffusion of the dopants can also be achieved through chemical vapor deposition (CVD), spray-on, spin-on, and screen printing technique. A uniform layer of dopants, that is phosphorus and boron doped oxide, can be deposited on either side of the silicon wafer through the CVD technique, which follows the drive-in step and provide much uniform profile and controlled dopant concentration. So the advantage is that the junction on the front side is made, while the disadvantage is that this process requires highly pure and expensive gases. Grid formation. So students, after junction formation, The next step is to form the metallic contacts on the back and the front side of the solar cell to collect the charge carriers, which is also shown in this figure. The materials used in grid formation must facilitate the good ohmic contact, low series resistance, good adherence, and good solderability. Most widely used materials for grid formation within silicon solar cells are nickel, gold, silver, titanium, palladium, and aluminium. So these are the materials which are used for grid formation. Now the techniques which are generally used to make the metallic contacts are electroplating, vacuum evaporation, and screen printing. Aluminium is used as a back metallic contact on the silicon p-type region and deposited by vacuum evaporation on the entire back surface. The aluminium is heated in a vacuum where it gets melted and vaporized, and then it is deposited on the cooler side of the solar cell. The front side of the solar cell is also deposited by vacuum evaporation, in which layers of titanium, palladium, silver are deposited one over the other. So first of all, a thin layer of titanium is deposited on the N layer of silicon, which gives a good adherence to silicon. After that, a layer of palladium is deposited, and at the end, a layer of silver is deposited on the front of the solar cell. The palladium layer between the titanium and the silver layers is deposited to prevent the electrochemical reaction, which results in the corrosion between the titanium and the silver. Later, the front contact is annealed at 500 to 600 degrees Celsius for 15 to 20 minutes, which makes good adherence and low contact resistance. The thick layer, that is silver or palladium tin, can significantly reduce the series resistance. This is the most common way to produce the solar cells of high efficiency. However, it is expensive as it is a batch process, and also it includes the expensive materials. Hence, now here the silver paste is used for the front metal contact and the aluminium paste for the back metal contact. The equipment used in this process is inexpensive, easy to maintain, and though a mask can also be done on the solar cell surface. However, the presence of oxide layer on the silicon surface results in poor adherence. The adherence can be enhanced by using a layer of palladium in between silicon and nickel, but the resistivity is decreased using solder coating. Anti-reflective coating. In order to avoid the reflection losses and to utilize more solar radiation, the anti-reflective coating (ARC) is an important part of a solar cell. Since the bare silicon has a reflection coefficient of 0.33 to 0.54 in the spectral range of 0.35 to 1.1 micron. The ARC helps in reducing the reflection losses and in lowering the surface recombination velocity. A single layer of ARC with optimal thickness can reduce the reflection to 10%, whereas 2 layers can reduce the reflection up to 3% in the desired range of wavelengths. The most common materials which are used as ARCs are SiO2, SiO, Al2O3, TiO2, Ta2O5 and Si3N4 in solar cells. These materials are deposited as ARCs on solar cell by vacuum evaporation process. Other methods of ARCs depositions include the sputtering, spin-on, spray-on, or screen printing. However, only the vacuum evaporation and sputtering gives good results. However, these processes are expensive. Furthermore, the average reflection can be further reduced by 2 anti-reflective coatings of different refractive index instead of using one reflective coating. This is also shown in the figure. That is, the exposed side coating has an index of refraction of 1.3 to 1.6, and the second layer placed in between silicon and the first layer has an index of refraction of 2.2 to 2.6. Hence, these two ARCs layers gives a better impedance match between the index of silicon and the index of air. So the schematic of the cell, the solar cell, after these above discussed parameters is shown in this figure. The module design or the conversion of the solar cell to a solar module. In order to get sufficient output power for a terrestrial application, the individual cells, each of 10 cm square to 100 cm square, are then interconnected in a series and parallel pattern as shown in this figure. That is, one module consists of 20 to 40 cells, and each may have 3 to 5 columns of cells in series or in parallel. A typical cell module containing 30 solar cells in series may give about 12 volts, which is very nominal, and 1.2 amperes, and a peak power of 18 watt, which is quite sufficient to charge a battery of 12 volts. Generally, solar cells are developed in a circular shape, hence packing density cannot be high, and 25% area of module remains uncovered. However, solar cells in the form of a square or hexagonal shaped avail better packing densities. Since the fabricated cells are thin, brittle, so they need to be protected from weather, and the connections are light and soft. Hence, these cells are encapsulated with a transparent cover at the top. This encapsulation provides the mechanical strength to the module and protects the cell from damage due to dirt, dust, hail, birds, foreign materials, moisture penetration, weather, and wind. Additionally, it also provides an electrical isolation to the voltages developed by the module. The material used for encapsulation must have life of more than 20 years, and it should be UV stabilized, should not increase the temperature of the cell, should have resistance to abrasion, should withstand the temperature in extreme conditions, and thermal shocks. The top cover should have high transparency for solar radiations, should be easily cleanable, and of course, it should be low in cost. Generally, the individual cells are encapsulated in inert filler between two clean and clear glass sheets. Generally, the front side is covered with transparent material, which is a UV stabilized plastic sheet, and the back side is covered with a plastic rigid plate.
So, students, let us summarize what we have learned in this module. Several advanced technologies have been developed for producing the low-cost silicon solar cell modules. Direct growth of silicon ribbons eliminated wafer slicing, which is the weak link in any ingot technology. The main requirements on techniques for fabricating a cell on silicon wafers are that they must be capable of a high degree of automation and they do not consume excessive material. The design of silicon junction solar cell has evolved from following characterizations. The PN junction has to lie close to the surface of the cell to give maximum current output. The excessive dopant concentration introduces the effects, thus causes the electronic properties to be less than the optimal. In the design of the top contact of the cell, the optical parameters determining the associated power loss are the contact layout, the sheet resistivities of the contact metal layer, and the diffusion top layer of the cell. A quarter wavelength anti-reflection coating can increase the output current of a solar cell by 35%. Thank you.